Hey guys, welcome. I think we can get started now. Well, today will be the second week of number theory, and I decided to do one more lecture as well this week, so there will be a bunch of number theory going on this week. Well, today I would like to talk more about Wilson's theorem, and then we'll also talk about Legendre symbol, so about quadratic residues. Let's get started. Well, I would like to start with the quadratic residues, with the Wilson's theorem, and then you will see that they're quite related. Well, so Wilson's theorem and quadratic residues. By the way, okay. Anyway, at the end of the lecture, I will let Jack to make an announcement about Math Club seminar. All right, so let's get started. Well, let me remind you the theorem of Wilson, which says the following. Well, it says that for every prime, okay, I'm going to write it like this, for every prime p, the number p minus 1 factorial plus 1 is divisible by p. So that's the theorem, Wilson's theorem. It's a very, very important theorem. So when you have something relating the factorial and you will want to prove something, some divisibility about the factorial, always think of Wilson's theorem. Okay. Now, in other words, we have that p minus 1 factorial is congruent with -1 mod p. So that's Wilson's theorem, basically, right? And now let me give you an example, a bunch of examples. We'll do some problems. In fact, let me start with, let's say, problem 1. And this will be a very classical problem. It's you can even find it in the book of Răzvan Jelka and Titu Andreescu, the Putnam and beyond. Well, the problem says the following: let P be an odd prime and we like to show that. So I'm just gonna show that 1 squared times 3 squared times all the way to p minus 2 squared is congruent with -1 to the power p plus 1 over 2 mod p. And then the second one, as you can imagine, 2 squared times 4 squared times p minus 1 squared. This will be congruent with -1 to the power I think there is a mistake. Anyway, p plus 1 over 2 mod p. Anyway, not sure if anyway, we'll see. So let's look at this, right? Well, you'll be the main idea here is to look at the following at the fact p minus 1 factorial. So I can write this in the following way. So that's the trick. I'm going to separate the odd ones and the even ones, let's say. So I'm going to do it in the following. So it's 1 times 3 times p minus 2, right? And then I'm going to just put here 2 times 4 times p minus 1, right? So this I'm going to write them. And by Wilson's theorem, this will be congruent with -1 mod p. So here I use Wilson's theorem. Right? So this is -1 mod p. But now, if we look at each term, let's say from the first parentheses, 1 is congruent with negative p minus 1 mod p, right? Obviously. Then what? 3 will be congruent with negative p minus 3 mod p. And we keep going, and we'll go all the way to p minus 2, which will be what? Will be congruent with negative p minus 2 mod p, right? So by multiplying all this, right? This okay, so this implies that, well, we're not multiplying yet. This implies that what? That 1 times 3 times p minus 2, right? This guy will be congruent with -1 to the power p minus 1 over 2, right? Times 2 times 4 times p minus 1 mod p. So now we're going to multiply this. So we have this congruence here. Now keep in mind what we are trying to prove, and I think that's a mistake there. It should be p minus 1 over 2, but anyway, in fact, let's see how we're what we will obtain at the end. All right, so we will have what? So now we're going to multiply this congruence by this product 1 times 3 times p minus 2. So we will have that. So multiplying the congruence by 1 times 3 times p minus 2, we get, so we'll get what? So we're going to get that p minus that 1 squared times 3 squared times p minus 2 squared is congruent with -1 to the power p minus 1 over 2. And here I'll have p minus 1 factorial, which will be -1 mod p, so -1 mod p. But this guy will give us nothing else than just what? Then, yes, it's exactly -1 to the power p plus 1 mod p over 2 mod p. And that's it, right? All right, so that's the first part, if you look at it. The second part, I'll leave it to you as an exercise. So the second part is the same thing. All right, so that's one application of Wilson's theorem. By the way, I have a question. Can you hear me well?
Yeah.
All right, that's great. All right, so that's the second part, we just reversed the first part and that's it. It's not a big deal. So instead of using these congruences here that I just mentioned, right? 1 is negative p minus 1 mod p. You use it for 2, for 4, for p minus 1, and that's it. So it's basically the same thing. So I will leave it to you as an exercise. Now let's see some other, so this is problem 1. It's pretty standard, I would say. So problem 2, By the way, Jack, in your number theory course that you took, did you guys cover quadratic residues in Wilson's theorem?
Which one? The undergrad one or the graduate?
The undergraduate one, of course.
Oh, yeah, we did.
Ah, you did. Okay, perfect. All right. Now let's see another problem, which it's a little bit has a more of a combinatorial taste, but anyway, the problem says, it says the following: prove that there are no positive integers n right, such that the set, and I'm going to look at this set, with 6 elements, n plus 1, n plus 2, n plus 3, n plus 4, n plus 5, right, can be partitioned right, right, into 2 sets with the product of the elements of one set equal to the product of the element of the other set, to the product of the elements of the other set. All right, I want you to look at the problem a bit for a couple of minutes. And of course, you see, it has a more of a combinatorial flavor, but the idea behind this problem is, again, Wilson's theorem. So try to think of something, maybe it has an idea, I would say. So what do you think? So you see, you have 6 elements, and now you're trying to use Wilson's theorem. So basically, you have to work mod a prime number. So what would be that prime number that will come into you, that you will think about? So let's look mod 7. So let's work. And you'll see why. Well, first of all, the first thing that we need to take care of, we can say that none of the 6 numbers is, let's say, divisible by 7. That's the first thing. So none of them is divisible by 7. And why is that? Why do you think is that? None of the 6 numbers is divisible by 7. Well, well, in otherwise, we'll have what? So if one of the 6 numbers is divisible by 7, then the product of the elements, right, of one in one set is would be divisible by 7, while the product of the elements in the other set will not. Well, this will not happen. In the other set. All right, that's good. So we know that none of these 6 numbers is divisible by 7. That is great. Well, now let's see. So by Wilson's theorem, right? So by Wilson's theorem, the product of 6 consecutive numbers, the product of 6 consecutive numbers is congruent with -1 mod 7, right? So we decided we're going to work mod 7. So this happens. And now we want to prove, keep in mind what we want to prove. We want to prove that there is no positive integer n such that this set can be partitioned into 2 sets such that the product of the elements in one is equal with the product of the elements in the other set. All right. And now what we're going to do is the following. So if such a partition exists, right? Let us denote by x the product of the elements in one set, right? Okay, so now once we have this, then this will imply that x squared, so we're going to take all the product, will be nothing else than just n times n plus 1 times n plus 2 times, okay, all the way to n plus 5. But we know that this is nothing else, is congruent with -1 mod 7, right, by Wilson. So this means what? And I'm going to say something here that we will be talking about in the second part of this lecture. So this means that, and I'm going to write it with red here, that -1 is what we will call is a quadratic residue mod 7. Right? So we say that the -1 is or a number A is a quadratic residue if it has is a solution of this congruence x squared is congruent with A mod prime P. So in this case, we obtain that -1 is a quadratic residue mod 7, which this doesn't happen, and we'll see which is false. So we get a contradiction. So the problem ends here. We will see, well, like I said today, I will show you why -1 is not the quadratic residue mod 7, and we'll talk about the Legendre symbol as well. Now, but before we go and dive into this, let me do two more problems. And in fact, I'm going to do another problem which will be translated in the language of Legendre symbol. So that's why I tried to do some kind of, well, I would say a prerequisite, but anyway, such as Wilson's theorem, so that you can see better what happens with the quadratic residues. Now, the next problem that I have in mind is the following. Well, let P be an odd prime number. Show that the equation x squared congruent with the -1 mod P. So in other words, we'll translate this as -1 is a quadratic residue mod P. So this, if this equation has a solution, if and only if P is congruent with 1 mod 4. So -1 is a quadratic residue mod P if and only if P is congruent with 1 mod 4. And we'll write this in terms of Legendre symbol. All right. Again, this is a pretty standard problem. And in fact, you can prove something similar if you replace -1 by 1 there, and then you'll have, instead of P being congruent with 1 mod 4, you'll have P congruent with 3 mod 4. But anyway, that's a very similar exercise that you can do if you want. So keep in mind that here we have to prove two ways. Now, let's prove it this way, this implication, from from right to left, right? Which says the following: if P is congruent with 1 mod 4, then this equation x squared is congruent with -1 mod P has a solution. Okay, so we want to prove this. Well, we can actually put our hands on such a solution. So we claim that x equals P minus 1 over 2 factorial is such a solution. Is such a solution. Is a such solution. All right. So in other words, we have to show that P minus 1 over 2 factorial is congruent with -1. This is -1 mod P. So how are we going to show this? So let's look at it. So how would you think we can show this? So we're going to use the same idea as in problem number 1, right? So we're going to separate, keep in mind there that we had the odd and the even factorials of numbers in that factorial. So we're going to do something that is pretty similar here. And what we're going to do is the following. So we're going to use again Wilson's theorem. So by Wilson's theorem, we have the following. So hold your breath a bit. So this will be -1, which is, I'm going to write it in this way, P minus 1, which is congruent with P minus 1 factorial mod P right? This is Wilson's theorem. But now this guy, p minus 1 factorial, I'm going to write it in this way. So now it's equal. So this is 1 times 2 times, and I'm going to write it all the way to p minus 1 over 2. Then I'm going to have p plus 1 over 2 going all the way to p minus 1, right? So p is not there, by the way. It's only p minus 1 factorial, which is 1 times 2 times p minus 1. And I'm going to separate it into these two. So I'm taking all these numbers all the way to p minus 1 over 2. And then from p plus 1 over 2 to p minus 1. So I'm going to separate it into these two classes. And this guy will be congruent, and I want you to be look carefully here, right? With what? With 1 times 2 times, and now I'm going to have p minus 1, right? And now I'm going to have here, everything will be p minus 1 over 2 times p minus 1, right? So, right, because I can write the second part now. So this would be, and which this would be, okay, mod p, let's see, sorry. And this guy will be nothing else than just negative 1 to the power p minus 1 over 2, right? By Wilson's theorem, times this guy, p minus 1 over 2 factorial squared mod p. Okay, so this, there you go. So p minus 1 factorial, p minus 1 over 2 factorial squared is nothing else than just negative 1 mod p. And indeed, this equation has a solution. Now let's see the other on the converse of this, which will be, well, we have to show that if that equation has a solution, then p is 1 mod 4. So let's assume by contradiction that p is not 1 mod 4. So its p will be 3 mod 4, right? That's the only option we have. And now assume that such a solution exists, and we know that such a solution of our congruence, such a solution exists. Well, let's call it A. All right. So this implies what? Well, now we're going to use Fermat's little theorem. So we know that. So by Fermat's little theorem, we have the following. I'm going to write it in this way. So 1 will be congruent with a to the power p minus 1 mod p, right? So we know this by Fermat's little theorem, right? But this guy is, I'm going to write it in this way. So this will be a squared times p minus 1 over 2, p minus 1 over 2, which will be nothing else. Since we know that this is a quadratic residue, so it has a solution, this will be nothing else than just, so a squared will be 1, so this will be, sorry, negative 1. So this will be negative 1 to the power p minus 1 over 2, which will be nothing else than just congruent with negative 1 mod p. which is false contradiction, right? One is congruent with -1 mod p, and keep in mind that p is congruent with 3 mod 4, so that's contradiction. And that's it. So you see, you have to put everything together with Fermat's little theorem and so on. All right. Now I have one problem in mind and this will be a little bit, I'll give you the main ideas. So problem 4, and this was a difficult one, I would say. And the statement is the following. So it was a Putnam B6, 2011, I think. Let me look. Yes, 2011. That was a very difficult Putnam, I would say, one of the most difficult Putnam exams. And the problem says the following: let P be an odd prime show that at least P plus 1 over 2 values of n in this set 0, 1, 2, all the way to P minus 1. Oh, okay, this rings a bell. This number, the sum from k equal, in fact, let me write it here. The sum of k factorial times n to the power k, and this guy goes all the way from 0 to P minus 1, is not divisible by P. Okay. I want you to look at it a bit, and we can let's analyze it together. Well, I would say it's very tricky. It's very tricky, but it has some idea. Maybe there is a way to express this guy here. Right? So that's the main idea behind these problems. Okay, let's see. So we want to look at that guy, at that sum, right? And we want to show that at least P plus 1 over 2 values of this in that for, wait, what? Show that for at least, show that for, my God, sorry about that. For at least, P plus 1 values of n in that set, this guy, that sum is not divisible by P. So the main idea is to look at that sum, and more particularly, we want to look at this guy inside the sum. You see, you have a factorial, and I just told you about that factorial, that when you see something with the factorial, and even if you have a sum, and of course you're trying to prove something which involves divisibility and so on, then you will think of maybe Wilson's theorem might be helpful here, right? So you would like to think this way. So let's see, now I want to look at that guy inside. But the way I'm going to look at it, I'm not going to look at it directly. So maybe I should do something. But before I want to go into this, I want to make a convention because at some point there will be some polynomials involved. Like I said, the problem is quite tricky. It's not as easy as you think. So I would like to make a convention. So we're going to, first of all, we're going to choose a convention. We choose a convention. And what we're going to do is the following. So on the convention, I'm going to, for the value for 0, 0 over 0, which you know it's indeterminate, but I will take it to be equal to 1. Right, so I'm going to make, I'm going to choose this convention. Because if I can also take 0 to the power of 0 to be 0, but if you look at it, the problem will not be valid anymore. Just take p equals 3. So anyway, but now, all right. So once I have this out of my way, I would like to use Wilson's theorem. But the way I'm going to use it is not the. Keep in mind that this n, that's another thing that I want you to look at. N is in this set here. So maybe I should, so now let's analyze this. So maybe I should look at, let's look at, let us look at this guy. And the way I'm going to look at is in the following. So I'm going to look at k factorial. And now I know that n goes all the way from 0 to p minus 1. Maybe I should look at p minus 1 minus k factorial. Okay, I'm going to look at this. These guys. So this will be, so by Wilson's theorem, okay, maybe I should put a dot here so that, so factorial. By Wilson's theorem, what do we have? We have that this guy k factorial times p minus 1 minus k factorial, right? This will be congruent with negative 1 to the power k times p minus 1 factorial, right? Because p minus 1 minus k factorial will be congruent with p minus 1 factorial, right? You can, it will be one of the terms. So that's the trick. But this guy, I'm going to use now Wilson's theorem. This will be negative 1 to the power, so you know that p minus 1 is congruent with a negative 1 mod p. So I'll have here negative 1 to the power k plus 1, right? So negative 1 to the k times negative 1 mod p. This is by Wilson's theorem, right? All right, so I have this. So maybe I should use this somehow. So now I'm going to have the following. So pay attention here. So we have, I'm going to look at this sum. So the sum from k equals 0 to p minus 1 of k factorial times n to the power k. Okay, I'm going to use this as a polynomial times x to the power k, right? So I'm going to use this as a congruence of polynomials. This will be congruent with the sum from k equals 0 to p minus 1, right? Of, so now I would like to use this k, okay. So this will be negative 1 to the power k plus 1, right? Over p minus 1 minus k factorial, right? So I can, you write it in this way, times x to the k, right? Mod p. Agree with me so far? So I just rewrote the relation that we got from Wilson's theorem. And now when I look at all this, this will be nothing else than just, so this will be congruent with, so let's see. So this will be, so let's look at this sum. So this will be what? Ouch. So this would be, if we look at it, okay, if we reverse this, so we, instead of writing p minus 1 minus k factorial, I'm just going to write k factorial. So I'm going to reverse this. This would be nothing else than just x to the power p minus 1 times the sum from k equals 0 to p minus 1, right? So I'm going to take, and here I'll have negative 1 to the k negative, oh, so it's going to be negative x to the power k, everything over k factorial. So it's the same thing, right? Mod p. And now what we're going to do is the following. So this is what we call a congruence for Laurent's polynomial. This is what of Laurent polynomials. Okay. And now what we're going to do is in the following. So now we're going to replace negative, so replace now negative 1 over, so replace x, let's say, with negative 1 over x. And our problem reduces to showing that the polynomial and now let's see when we look at this, so the polynomial will be, and let me denote this by g of x. So I said I'm just gonna, so it will be the sum, and this is a very classical problem, from k equals 0 to p minus 1 of x to the k over k factorial, this guy. And pay attention, this will be mod p. So instead of writing this mod p, and I said this showing this polynomial over fp, keep in mind that this fp consists of all numbers mod p, so it will be 0 all the way from p minus 1, has at most p minus 1 over 2 non-zero roots in fp. That's what we'd like to prove. And this is a very standard problem at this point. Well, when you have to show that something, the only difference is that this is actually, it's a very, very standard problem. The only difference is that the standard problem is not in FP, it's over for real numbers. Anyway, we'll do that when we'll be talking about analysis. But anyway, let's do it in this situation. So we have to show that this has at most p minus 1 over 2 non-zero roots in FP. Well, like I said, the standard, so we're going to write the following. Write h of x as x to the p minus x plus g of x. And now we're going to take the derivative of this. So the derivative of h is given by, so this would be h squared, oh, h prime, sorry. This will be nothing else than just p x to the p minus 1 plus g prime of x, right? Okay. But now, if we look at this, but also keep in mind that we are in FP, right? So something wait, let me see. So wait, let me see. Okay, so we're in FP, so this guy will be nothing else than just -1 plus g prime of x. And now I'm going to write it. Okay, let me just write it. Because so which will be equal to -1 plus, and g prime of x will be k, so it will be the sum from k equals 0 to p minus, let me see, p minus 1 of k x to the k minus 1 over k factorial. All right. So this would be -1 plus the sum from k equals 0 to p minus 1 of x to the k minus 1 of k minus 1 factorial, right? Okay. Great. And now if we write the first term, so this would be nothing else than just, so we can write this, if we leave the terms for k equals 0, so we're going to make this convention. So we will have that. Okay, so this will be written as the following. So h prime will be 1 plus the sum from k equals 1 to p minus 1 of x to the k minus 1 over k minus 1 factorial. Okay. And this guy will be, also, we can write this as x to the power p minus 1. So again, we have used Wilson's theorem. So this will be plus g of x. And now, so we have this. Now, if we have a 0, if, let's say, a number alpha in FP, right, is a 0 of g. So in other words, g of alpha is 0. Okay, then this guy alpha is different than 0, right? Because keep in mind that g of 0 is 1. All right. So we have that. Let's see, what do we have? So we have that alpha to the power, what do we get? Okay, so alpha to the power p minus 1 will be 1. So h of alpha will is the same as h prime of alpha, and it's 0, right? So alpha is at least a double root, is at least, well, I'm appealing to some. So when I have alpha, it's the h of alpha is 0, then the first derivative is 0, then alpha is at least a double root. If is at least a double root of H, right? Well, since H is a polynomial of degree, since H is a polynomial of degree P, then at most, then there are at most P minus 1 over 2 zeros of G in FP, and that's it. That was the problem. I'll redo this problem again in a different circumstance. Well, I'll look at this guy here. Oops. I'll show that something happens with this polynomial about and relating its roots. Anyway, that was these are the problems that I wanted to show you. Now, since I have some time, I would like to talk about quadratic residues. I know I'm going very fast, but this will be recorded and you can watch this afterwards and you can ask questions if you want. We can, now I would like to talk about quadratic residues. So those of you who haven't not taken a number theory course so far, you'll find this something new. Well, let's see definition first. I would like to come to do some definitions because this is not quite like Jack, I have a question. Did you guys do this at the end of the semester or? Did you discuss about quadratic residue at the end of the semester of the number theory course or?
Yeah.
So it was at the very last thing.
Yeah, we did quite a bit with it.
Ah, you did quite a bit. Ah, okay. All right. So let's see what the quadratic residue is. I already said a few things about it, but well, you can also consider quadratic residue modulo an integer, not just a prime. So I'm just gonna tell you the definition, more general definition. So I'm gonna consider let A and M, right, be integers, and not just gonna be just positive integers. Integers with M will be greater than 1, right? We say that the number A, we say that A, okay, let me write it with a different color, that A is a quadratic residue mod M, keep this in mind, right? If there exists an integer x, if there exists an integer x, right, such that this equation x squared is congruent with A mod M, right? So in other words, this equation x squared is congruent with A mod M has a solution, right? So there exists an integer x such that x squared is congruent with A mod M, right? So, and okay, and we say that, moreover, we say that A is a quadratic non-residue. Say that, okay, let me write it in this way. A is a quadratic non-residue non-residue mod M otherwise. So when I say otherwise, I mean that there is no integer x such that x squared is congruent with A mod M. And now I'm going to define the following. So we're going to write this in a certain way, and I'm going to define the what we call a Legendre symbol. So there is a way to write this quadratic residue. And the way we're going to do it is, so let's call this definition 1, definition 2, and then I'm going to give you an example. Legendre symbol. So there is a way to write this quadratic residue. And in fact, there is also a Jacobi symbol, but I'm not going to talk about this. I'm just going to stick to Legendre symbol. I think it's already too much. All right. It says the following. Let A be an integer and P is a prime. Is a prime number. So we define the Legendre symbol, define the Legendre symbol as the following. And I'm going to define it in this way. Okay, so it's going to be A by P, Legendre symbol A by P. So I'm going to read it in this way, will be 0. In fact, let me write it with a different color. So A by P will be 0 if P divides A, right? Will be 1 if A is a quadratic residue mod P. And -1 if A is a quadratic is a non-quadratic residue, is a quadratic non-residue mod P. If A is a quadratic non-residue mod P. So this is how we define the Legendre symbol, and I'm just going to give you an example now. Right, look at the definition, and I'm going to write it. It's a very nice way to write quadratic and non-quadratic residues, and then I will show you some of the criteria. And but now let me give you an example. So the example I have in mind, I think I have it here somewhere, but anyway, this is a simple one, is the following. So now, so example, let me take P equals 7. So we want to see which one are the quadratic residue, and A will I'm going to take all these integers 1, 2, 3, 4, 5, and 6. So I want to see which one is a quadratic residue, which one is not a quadratic residue. Keep in mind that a number A is a quadratic residue if there exists x, an integer such that x squared is A mod P. So let's see. Let's look. 1 squared is 1. So this is 1 mod 7. 2 squared is 4 mod 7. So now I'm going to take 3 and I'm going to compute the square. So 3 squared is 9, and 9 mod 7 will be what? Will be 2 mod 7. Now let's take the 4 squared is 16. 16 mod 7 is what? Is again 2. Right? Now let's take to 5, so this will be 25. 25 mod 7 will be 4 mod 7. Now let's see the last one. 6 squared will be 36. 36 mod 7 will be, what is 36 mod 7? So 7 times 5 is 30. Okay, so it's 1 mod 7. All right. Now, if you look at this, can you identify which one is a quadratic residue and which one is not a quadratic residue? Can you tell me that? Which numbers from here are quadratic residues, mod 7, and which one are not? So from this list of A, 1, 2, 3, 4, 5, and 6, which one is a quadratic residue? Which A do you see on that list? If you look at it, it's only 1, 2, and 4. That's it, right? You look at this list, you see only 1, 2, and 4. So in other words, if you want to write this in Legendre symbol, you can say that Legendre symbol 1 by 7 is 1. Legendre symbol 2 by 7 is 1. And Legendre symbol 4 by 7 is 1. The others will be, based on the definition, will be -1. So 2 by 7 is, 3 by 7 will be what? -1. What else is there? 5 by 7 is -1. And 6 by 7 is -1. Right? And now I would like to go back, since we consider mod 7. As you can see, the only numbers that are quadratic residues mod 7 are 1, 2, and 4. And now remember, I want to go back to our problem. There was a problem, the problem with more combinatorial flavor. Look at this guy here. -1 is a quadratic mod 7, quadratic residue. Well, -1 in mod 7, imagine that it's like 6, right? 6 mod 7, it's a quadratic residue. In other words, 6 by 7, it's 1. But in fact, as we can see, is not 1, it's -1. So it's a quadratic non-residue, right? 6 is -1 because it's a quadratic non-residue. Guys, is it clear for those of you who haven't taken any, is it clear, the example? Chris, Abby, Caroline, what do you guys think? Is it clear? And anyway, you can play with any other. For example, you can take a prime, let's say 5, if you want to play around, and you'll take the numbers 1, 2, 3, 4, and you like to do the same thing. Anyway, so that was just a small example that I wanted to do. Now, well, this is the Legendre symbol. It's a very nice way of writing quadratic residues. And now let's see some of the properties of this. Well, before I even go into this, let me show you that there is this theorem. It's a very important theorem. Which says the following. The theorem says that if okay, let P be an odd prime, then there are P minus 1 over 2 quadratic residues, and in the set 1, 2, 3, all the way to P minus 1. And of course, there are P minus 1 over 2 quadratic residues. All right, now let's see some properties of the Legendre symbol. In fact, let me write it here. All right. So we would like to see how we can operate with the Legendre symbol. Well, the first property is that if, let's say, A is congruent with B mod P, then the Legendre symbol, okay, I'd like to add something here, and AB, the product, is not divisible by P, then the Legendre symbol A by P is the same as the Legendre symbol B by P. So that's the first property. The second one, well, the Legendre symbol is multiplicative. So in other words, so the AB, Legendre symbol AB by P is the same as A by P times B by P. Is multiplicative. Okay. The third property, well, if P is an odd prime, so in other words, let's say P is different than 2, then Legendre symbol negative, so negative 1 by P is the same as negative 1 to the power P minus 1 over 2. The fourth one, again, if P is different than 2, then 2 by P is the same as negative 1 to the power P squared minus 1 over 8. I think this is, I don't know, Gauss proved this. I don't recall exactly who proved it, but anyway. Anyway, you will see something more general by Gauss reciprocity theorem. We'll go there. Another one which is very, very important, and now let me write it in red. If, let's say, P does not divide a number A, and P is not, again, is an odd prime, then by the way, I forgot to specify, but P here is a prime number so that you know. Then we have the following: A to the power P minus 1 over 2, so this is Euler's criterion, is congruent with A by P mod P. So this goes to Euler. My goodness, how many things Euler did in his life. Basically, he laid the foundations of the entire mathematics. And now there was another, let me see, okay, before I go into, there are some other things I'd like to say. Let's see. Okay, 6. Okay, these are important as well. So if P is an odd prime, then we have the following: negative 1 by P. We can actually say who this is 1 if P is 1 mod 4, and we have already seen that, and negative 1 if P is negative 1 mod 4 or 3 mod 4, right? We actually proved this. And then another property which I would like to say is the following: if P is again an odd prime, then 2 by P will be 1. So 2 is a quadratic residue mod P if P is congruent with plus minus 1 mod 8, and negative 1 if P is congruent with plus minus 3 mod 8. So these are the things that there might be very useful. I'm not going to go into the proof of this because I don't want to lose time. And now what I would like to do is I hope I'm not forgetting anything. 8th, this is a very important, and the proof is quite difficult, is what we call the quadratic reciprocity law of Gauss. And it says the following: if P and Q are distinct prime numbers, then we have the following. Then we have that Legendre symbol P over Q times, or you can times Legendre symbol Q over P is the same as -1 to the power P minus 1 over 2 times -1 to the power Q minus 1 over 2. So this is Gauss reciprocity law. Okay, quadratic reciprocity law. That's an amazing thing. You should keep this in mind. This is, let me see if I, this is a, yeah, that's the statement. Yes. That's the statement. Okay. So basically, these are the properties of the Legendre symbol, everything in a nutshell. And now what I would like to do is just to give you a very, very simple example. You see, I would like to, that Euler's criterion here that I just mentioned, you see, where is it? Okay, this guy here, right? As you can see, it's just an application of combination of Wilson's theorem. So when I say property number 5, it's just a combination of Wilson's theorem and Fermat's little theorem. And, yes, Fermat's little theorem. All right, now let me give you a quick example. Well, unfortunately, due to lack of time, I'll give you a quick example and then I'll leave a problem to you. Maybe I'll cover this problem in one of the recitations, but I'll leave it to you. But before that, let me do this quick example. The question is the following: is 3 a quadratic residue mod quadratic residue mod, let's say 79? That is a question. What do you think? In other words, equivalently, is there a solution to the equation x squared congruent with 3 mod 79? Okay, these are very standard. So Jack, I think these were the kind of problems that you guys used to do in the number theory course, right?
Yeah, in our undergrad one, we did stuff like that.
Yeah, I mean in the undergraduate one. I'm always referring to the undergraduate one. Yeah, so these are the type of problems that you, anyway, so how would you do this? Well, as you can see, the 79 is a pretty large number, and I don't want to do any brute force as we have done in the previous example, right? We checked all the squares all the way to 79, but to 78. Imagine doing this take all the numbers from 1 to 78 and do this. That would be, don't do that. So that's why you need to use the properties of the Legendre symbol. So don't use brute force. And so we're interested in using this guy. So 3 by 79. But now what you can do is the following. So we're trying to get some information about this guy, right? Okay, so let's see. So But you see, there is no way you can. So maybe we should use the, so by the Gauss quadratic reciprocity, we have that. So what do we have? We have what? We have that 3 by 79 times 79 by 3. So the Legendre symbol of this will be what? Will be negative 1, 2. So p minus 1. So it will be 3 minus 1 over 2 times negative 1, 2, 79 minus 1 over 2, right? So that's what we know about the, okay? And this guy, if you look at it, so negative 1, negative times 1, this will be negative 1. Okay. And now let's look at this guy 79, but we know that 79 is what? Is mod 3 is 1. So it's 1 mod 3. So 79 is a quadratic residue, is a quadratic residue mod 79. In other words, say that
I
again.
have to go. So I was wondering, what was Jack's announcement?
Okay, so Jack, can you make the announcement?
Yeah. So tomorrow, the Math Club is hosting our first seminar of the semester, and our speaker will be our very own Cezar. He's going to be giving a talk over some problems that are equivalent to the Riemann hypothesis, and he'll be going over some fun stuff with that. So the talk is tomorrow at 5, and it'll just be with the same Zoom link, I believe. And then if you want more up-to-date things on what's happening in the Math Club, you can go ahead and join our Discord, where we post frequent updates about what's going on, and we also discuss math. So I have posted that link in the chat. You can copy it and join if you want. That's all I have. Hope to see you tomorrow.
How long are you growing your hair out?
Oh, yeah, it's pretty long now.
Yeah, it's nice. Okay, bye. Thank you.
All right.
Bye.
So let me just finish this problem. In fact, I think you can do it. It's at this point. So we know that 79 is a quadratic residue. Wait, what? What am I writing here? So 79 is quadratic residue mod 79, mod 3, sorry. Okay. So 79 by 3 is 1, right? So this means that what? So finally, thus we have that 3 by 7, the symbol Legendre 3 by 79 is negative 1 times 79 by 3 to the negative 1, which is negative 1. So this means that, so 3 is not a quadratic residue. Mod 79, and that's it. Anyway, this is pretty standard problem. And now I would like to just do 1 second. I would like, there was this problem, I don't know, and I'll solve this in the recitation. So this was in Vietnam Olympiad or something like this for students, I think. They have some kind of, which says the following. It's a very nice problem, and I'll leave it to you to think of it. So prove that this number 2 to the power n plus 1 has no prime factors of the form 8k plus 7. So keep this, so try to think of this problem. It uses basically the properties of the Legendre symbol. So try to interpret this in terms of the Legendre symbol. Okay, guys, I think I'm gonna stop here. Next time we will do, well, I'm gonna do another video lecture where I'll be talking about probably some kind of Diophantine equations and then some analytic methods in number theory. All right, thank you.